The title is Resolving Disagreements by Sharing Uncertainty. What I think is a good starting point for this is concepts like this advert in which I saw in London Bank Station in 2012. This was a Skype advertisement campaign, and what it says is why work alone when you can collaborate. The idea is very simple and straightforward. Skype is trying to tell you that doing things together with others is better than doing them alone. We give you the option, the free and available option of working with whoever you want on the planet, so you should never work alone. And if you look at the life around yourself, you will see that collaboration is everywhere. It seems like something everybody completely agrees with. But one of the interesting points about this is that if you actually put a question mark on this and ask, should we collaborate at all? And look at the history of sociology and psychology of this question, you will see that this matter is far from resolved, and the dogma that I tried to demonstrate in the previous slide is quite misguided. Even in popular wisdom, you have aphorisms such as two heads are better than one, from, I think, the Ecclesiastes, Bible, and too many cooks spoil the broth from popular culture. We even have similar aphorisms in Farsi, if you like the things with too many, raising too many watermelons with one hand, it's impossible. Or there's even verses from Holy Quran that say that true believers in God do everything after talking to each other, and vice versa. So all of these notions are everywhere, but the opposite is also always around. So the fact that people are the suspicion against like working with everyone and cooperation is not new. There are several examples. One of them is this great book, Extraordinary Popular Delusions and Madness of Crowds, by Charles Mackay from 1842. It's still a bestseller on Amazon if you go. There is a very interesting chapter on facial hair in men, which quite applies to hipster cultures right now as well. If you look at, if you read that chapter, it's exactly like it just completely applies to what you see in East London these days. And then there is also the other books and everything. But we also have on this side concepts like the Condorcet jury theorem and Francis Galton's work on joint decisions or joint estimates by numerous people. Perhaps the two phrases that have been most successfully popularized are the madness of the crowds, which Charles Mackay used in 2 centuries ago, and opposite to that, James Surowiecki in 2005 published this book, Wisdom of the Crowds. And these two, again, show you they did the kind of tension between these two questions. So for us, one of the questions in our lab is, what makes a cooperation good or bad? How do we go from too many cooks spoil the broth to two heads are better than one? What are the characteristic or the limit conditions that put the cooperation under one regime or the other? Can we, most importantly, can we a priori decide if a given cooperation is going to be successful or not? And in order to do that, before doing that, what I will show you in the talk is going to be roughly in 3 sections. One is I'll show you our laboratory model of how we approach this question, how we quantify cooperative behavior and decision making. And then I will go on to demonstrate some of the features and hopefully give you 1 or 2 of those limit conditions. Then in the second session, I'll talk about equality bias, which is one of those things that I believe a lot of people, many of us believe, which affects and behave according to, which affects the consequences of collaborative decision making. And we will also finish by looking at the role of social influence and how equality bias and social influence can actually, again, moderate each other in order to impact collaborative decision making. So before going, what kind of laboratory model we use for that? My background, my PhD was in perception and in visual perception. So I did all of my PhD on contrast sensitivity and visual search and things like that. So in 2008, when I went to Denmark and started this line of research, the best thing I could do was to introduce what I knew how I could do, which was perceptual decision making, into addressing this question. And anybody who has gone through like Perception 101 in a psychology course, first thing that they teach you is that perception is noisy and incomplete. The best example for that, which is very appropriate for these days, is refereeing decisions, especially in football. These are three of my favorite examples. This is England versus Germany in 1966. Nobody knows if this ball actually crossed the goal line or not. The Russian linesman did actually, and that's what they say the English actually got the World Cup with. It's funny that they were having this kind of fight 2 weeks ago, last week.
La mano de Dios, no?
Yes, this is the mano de Dios, Diego Maradona and England again. And this one is 2010, Germany against England again, the other way around. This time the ball did cross the goal line, but the referee didn't see it. And England lost badly. This one is the most recent one, happened 3 days ago. Does anybody know which game this is? This is Copa America, Brazil versus Peru. And the goal was conspicuously scored by another hand of God. But so the referee made this mistake. And it is important to note that football decisions, refereeing football decisions, are very, very important decisions. And they have like massive consequences. I think last time when England didn't make it to, which one of them was it? Was it Euro 2004 or later, 2006? I don't know. Like the total loss to the English economy was something close to £1 billion. So you can see that these kind of things and that noisy perception can actually have very grave consequences. So the question we started with was, can cooperation between, for example, two referees enhance perceptual decision making? Can two referees do better than one referee? And in the case of FIFA right now, the question that was asked a few years ago was, we already have 3 referees. If we increase to 5, one behind each goal line, what is the expected added accuracy that you would get? Is it worth having 2 more people? And this question is basically trying to approach that. Like if we go from 1 referee to 2, how much of a benefit do we expect to get? If we go from 2 to 3, 3 to 4, etc., what is the quantitative benefit that we expect from having additional decision makers involved in an uncertain decision? So in order to test that, what we do is we measure visual sensitivity to contrast. This is what our lab looks like. We have 2 tables put at right angles to each other. The same computer is connected to 2 display screens. And 2 people sit at a right angle to each other so that they cannot see each other's screen when the stimulus is on the screen. But they can talk to each other, they can turn to each other when we give them the opportunity to talk to each other. This is what happens in the very initial examples of our experiments. We ask people to do a very basic classic sort of visual search task. This is called a 2-interval forced choice contrast oddball search. It's 2-interval because across time, which is this axis, we present 2 stimuli, one after another. This is the fixation point, the central cross at the center of the screen. Around that central cross, in each interval, we present 6 items. These are contrast sinusoidal, the 2-dimensional sinusoidals that are enveloped by Gaussian. So, and one of these 6 items has higher contrast. The blacks are blacker, the whites are whiter. And that dotted circle around it is actually not in the actual stimulus. In one of the two intervals, one of the 6 items has higher contrast. We call that individual higher contrast item the oddball item. The question for the observers is, in which interval did the oddball appear? 100 milliseconds of this one, 1 second of blank, another 100 milliseconds of the second one, and then after that, the answer, first or second. And what we can do with this is that we can increase or decrease the added contrast needed to distinguish the oddball from the distractors. And by systematically doing that across, let's say, about 300 trials, we can measure the subject's individual sensitivity in telling the difference between the signal and the noise. And the oddball would be randomly in one of the 2 intervals, and its spatial location also will be randomly chosen across the 6 possible locations. And we will see what the data looks like in a second, but after people have made, in this initial form of the experiment, first people made an individual decision, first or second, without talking to each other by pressing a button on the keyboard. Then the computer announced the choices, and the choices were color-coded so that everybody knew that for example, each subject knew which one has given the first and which one has given the second as their choice. After that, if they disagreed, which is in this case, the computer prompted them to talk to each other and make a joint decision. And in odd and even trials of disagreement, the color code would also tell them which one of the 2 people is in charge of inputting the joint decision to the computer. And finally, at the end of a given trial, we would tell them who was right, who was wrong, and whether they made a joint decision, and whether the joint decision was correct or incorrect. Anything unclear about this part? All happy? All right. So what we have, we can skip that one. We will come back to that comment at the bottom. This is how the raw, well, not exactly the raw, but the data looks like before we actually apply our models. So on the x-axis, we have the contrast difference in the target position. This contrast difference can go from about minus 15% to plus 15%. Minus 15% would mean the contrast oddball in the contrast oddball was in the first interval, and it was very obvious and very clear because there was 15% contrast difference between the target and the distractors. And like the 15% contrast is actually quite a good, easy to see difference. So this is targeting the first interval, very easy to see. This is targeting the second interval, very easy to see. And then as we get closer to 0, the difference between the target and the distractors becomes more and more and more difficult. On the y-axis, we are plotting the probability of choice reporting second interval. As you can see, when it is easy and in the second interval, people almost always report the second interval. 100% probability of reporting second. When it is easy and in the first interval, people in this experiment have been reporting, have never been reporting second interval. And as we get closer to 0, people's responses become more noisy and closer to 50-50. Around 3%, these subjects are about 50-50%. Now,
say again what the color was?
Oh, I haven't told you what the color code is. So the color code for the 3 sets of data points and curves refers to the subjects, the 2 people who are working together. Blue and yellow are the 2 people, and red is the color code referring to the joint decisions, right? So what we have here is what we in the present practice of perception, we call it a psychometric function. The good thing about this psychometric function that relates choice to stimulus is that we can quantify by fitting a cumulative Gaussian or any other sort of, like sigmoid for that matter, but cumulative Gaussian is good for our purpose here. We can quantify 2 very important decisional parameters. The most important one for us is the slope of rise of these curves. The slope of this rise shows us the subject's ability to distinguish between signal and noise. So imagine a perfect subject. The perfect subject would be constantly reporting first interval for all negative values, and then suddenly as a step function would go up and always report yes for all positive values. There would be a near infinity slope at the inflection point. A subject who actually is blind would be 50-50 for all decisions, would have a slope of 0. And any the higher the slope at the inflection, the better the subject's ability to distinguish signal from noise. The other factor, which I will not be focusing on today, but we could have a chat about if you want later on, is the inflection point, the position of the inflection point on the x-axis. That gives us the subject's bias in choosing first or second interval. If a subject has a bias for choosing one of these two more than the other, then the subject's psychometric function will be shifting horizontally along the x-axis. For example, a subject who has a higher tendency to report second would start from here, but would quickly go up, and the inflection point would fall, for example, somewhere around here, and vice versa for one who has a bias for the opposite. Right? Is this clear now? Okay, so from now on, what we will be doing is that we will use this kind of interpretation of the data, and these data points, by the way, these 8 data points that you see are data points that are drawn from various values that we have given to the additional contrast for the contrast oddball. As I said, for example, these data points, we vary the contrast of the oddball in 8 separate data points, in 8 separate steps, and then we bin them according to how much of a difference was there between the target and the distractors. All right? And finally, we fit the cumulative Gaussian. So what we measure as a quantitative metric of group success is the slope of the red curve at the inflection point, what we call the S of dyad. The ratio to the slope of the better member of the group. That's why we call it S max. Of every 2 people, one of them inevitably will have a somewhat better performance compared to the other one. The one who has a higher rising slope, which in this case is the blue curve, will be our S max. And the other one, the yellow curve in this case, will be our S minimum. So by this definition, what we are saying is that this ratio gives us a quantitative measure of how well the group would do if they actually bother to talk with each other and make joint decisions, rather than the better person just taking care of all decisions and dominating the conversations entirely, which would be some sort of an expert rule, if you like. Anyways, so this would be our main behavioral metric for many of the data that you will see. So back to the question, could uncertain individual decisions be improved by collaboration? The first answer to this question would be, we want to see if on average the slope of the red curve is bigger than the slope of the better member of the group. And in our first slide, in our first slide of results, I'm actually plotting those two separately rather than their ratio. So this is the S max, averaged across, I think here, 40-something people. And this is the empirical slope, the slope of the empirical curve that we get for each group, that red curve. And as you can see, the group does a better job compared to the better member of the group. And we can say that yes, it is possible to get a better perceptual decision, uncertain perceptual decision, by having people talk to each other. Any questions here?
So, sorry for interrupting, were the subjects tested first before the experiment to see if they had equal levels of visual perception?
For this experiment, the good thing is, because of this step, we actually have their individual independent decisions first. As a consequence, we know that their individual independent decisions have been measured for each stimulus separately, right? And that we take as our measure of their individual ability. And then we calculate the joint decision sensitivity from here. But if, like one may say that the benefit we see here comes simply from having to make a second decision twice, right? If that was the case, if simply making a decision first and then doing it a second time, that revision would allow you to do better, then people should be able to have the same result, even if we did not allow them to talk to each other, but we asked one of the two to make a second decision every time they had a disagreement, right? We have done that control in our first round of these experiments. And if you don't allow people to talk to each other, this benefit completely vanishes. So it is necessary for people to actually talk to each other. And having just a second chance to revise your decision when you see somebody else's disagreement will not give you this benefit. Which is also like informative by itself, because disagreement is also an indication of uncertainty. If it turns out that there is a decision in which you and your partner disagree, then having a chance to revise may actually help you do better. But what we have shown is that at least in this paradigm, the talking to each other is necessary to get this benefit.
Sorry.
Yeah?
I suppose the same pair repeat the experiment multiple times, but you do not consider getting better and better in time as a factor yet.
Well, what we have done is that rather than testing them multiple times, we have done running averages under collective benefit. And the running average asymptotes very quickly. And like you don't get any better after about 50 trials of practice. That's what we have seen. And 50 trials of practice takes something like half an hour.
Okay.
Yeah.
Sorry, one more point. You move a very wide range,
right.
and the camera doesn't capture the whole range.
All right, I can stay. This side is better than the other one. Okay.
Sorry for that.
No, that's okay. All right. So where are we? So two heads are better than one. We know that. Now the question is, what strategy do people use? Can we actually make some cognitive, some inference about the cognitive events that go on between people when they actually make these decisions? So the strategy we have taken to understand what people do when they make decisions is that we have tried to come up with several alternative models of what the communicated information is and what the applied decision boundary to that communicated information is. And then we try what we do is we infer from that communication rule and decision boundary rule what we expect the upper boundary of cooperation to be for each of those models, and then we compare those models to the actual performance of the subjects. I will go through these models one at a time. They start from easy, trivial ones, but hopefully we get more and more like sophisticated as we go through step by step. The first one is if only decisions were communicated. If every time there is a disagreement, what we only know is that we have a disagreement and we need to do something. If this is the case, and every time that would mean the decision rule for joint decision making would be to flip a coin. Whenever we have a disagreement, but we have no information about the uncertainty of the decision makers, the only way to actually arbitrate between them would be arbitrary. If we do that, the coin flipping would expect the expectation would be that the dyad would not do better than the average of the two people. Now, what if people disagree, communicate their disagreement only, but they also keep a memory of the previous feedback? We call this the behavior and feedback combination model. So that every time we make a joint decision and it turns out that Taha was correct and I was wrong, then we keep that in mind. Next time, if there is a disagreement, I defer to Taha. If we get that perfectly, and by combining feedback, we can perfectly understand which one of us is better, then we would have an exact expert rule. And that expert rule would mean that the slope of the dyad would be equal to the maximum of the two. So that's by communicating only the disagreement and having a perfect memory. What we saw during the experiments, our observation was that actually people communicate their confidences to each other. And the interesting point about this, that one of the more counterintuitive things that I observed when I was sitting in those experiments at the beginning was that initially people would try to distribute the labor. Someone would say, you look out for the target in the first interval, I look out for it in the second interval. Or some people would say, you take care of the upper part of the visual field, I take care of the lower part, left side, right side. But after 2 or 3 trials, people would abandon these strategies, and they would just communicate, how sure were you, or do you think you were certain, etc., or say, I think I got this one perfectly, and so on. So they would drop any of these spatial or temporal like division of labor strategies and would concentrate on communicating their confidence. So in our next model, we wanted to see what kind of information is it that the confidence is communicating. And the model that we came up with was mostly inspired by my colleague Peter Latham from Gatsby Neuroscience Unit. And it goes like this. So we have a very good demonstration of it, illustration of it from a commentary that was written on our paper. Actually, this is not from our own papers, but I've just stolen it. So imagine that we have the football situation. We have the 2 referees looking, or having just looked at the ball, hit the ground somewhere close to the goal line. We don't know if it was a goal or if it was not a goal. The blue referee thinks that it wasn't, and the red referee thinks that it was. We can think of their sensory evidence for these choices that they have made as Gaussian distributions, or as random variables drawn from a Gaussian distribution. For the blue subject, the mean of that Gaussian distribution falls outside of the decision boundary, which is why he believes that there was no goal. For the red one, it falls inside. And so the mean is telling us, or the sign of the mean is telling us the choice. And the larger the distance from the boundary, then the more vivid the perception or the experience of the observer who has seen the situation. But at the same time, there is also the issue of the variance of this distribution. So the blue subject in this case has a much tighter, much more precise set of sensory samples from what happened. And therefore, one could say, if we wanted to compare the precision of the choices that have been made, we could say that the choice made by the blue observer in this case is expected to have higher precision. So what we proposed was that the confidence is a combination of how vividly the subject has seen the target and how precise his perceptual representation of the information was. And the best thing we could come up with was the z-score of this distribution, the ratio of the mean to the standard deviation for that hypothetical sample from the random distribution. So now, where exactly would that happen in the brain? What would be the implementation? What would be, whether these would be neurons, whether these would be the retinal information? We don't really care about that. What we think about, what we go from is, we go from these assumptions, these very simple assumptions about the sensory evidence, to seeing what we can do, estimating or predicting the joint decision slope from these individual ones. The good thing about this representation for evidence is that if we actually think of their evidence as Gaussian distributions, then we can relate it very straightforwardly to the behavior that I have shown you already, which we fitted with a cumulative Gaussian. So across the many experiments, across the many trials, we can estimate the precision of this decision by looking at the slope of that drop. The higher the precision, the steeper the rise of that psychometric function. So if we do the math, one thing that we would need is if people communicate the z-scores, which are signed, and the sign indicates the choice, then we would have a very simple decision boundary. The decision boundary would be to compare the sum of the z-scores to 0. And if we write down these and write down the integrals, then we can, from this decision boundary, we can infer the expected slope of the weighted confidence sharing model. And why we call it the weighted confidence sharing, because this is the decision that is arrived at by weighting your choices by the confidence of your choices. So whoever has higher confidence dominates the choice. And it turns into actually a very simple, straightforward linear combination of the two. Now, we can get one step even more sophisticated than this. We can say that our two referees with their Gaussian distributions may be able not only to communicate their choices, but they may be able to communicate the mean and the standard deviation of the choice separately and separately. In other words, for example, in this kind of a slightly strange hypothetical situation, I could say, first, the contrast I think was 5 units and my variance is 10 units. We don't know how that would be implemented by language, but hypothetically, you could think of somehow maybe the language is capable of communicating this information. And the reason why it's a plausible model is that this is what your brain does in multisensory integration. So when you're listening to me and watching me speak, you're doing a speech recognition. A speech recognition is a prime example of multisensory integration. In multisensory integration, you combine information from different senses by combining the values you get from different modalities and taking into account the variance within each modality. And you have these information separately, and your brain can actually combine them optimally. If we do that, then we can do even better. We call this one the direct signal sharing. And by that we mean, rather than doing the z-score, the communication would communicate the mean and the standard deviation separately from each other. And if you do that, then the expected slope of the group is even better than the previous case. Now, how do they compare to each other, these four? In order to compare the four models with each other, I've plotted here the ratio of the slope of the worst member of a group to the better member, S min to S max, and we call this relative sensitivity. The reason why I have done it is that it gives us a very well-behaving metric for similarity between the competence of the two members. That goes from 0 when one person is very good and the other one is very bad. That is when S max is much bigger than S min, to 1 when S min and S max are almost or are exactly equal. So perfect similarity and almost no similarity. And this relative sensitivity is a measure of the similarity of competence between the two opinions. On the y-axis, I'm plotting the collective benefit, which I've already previously described to you. Now, anything above 1 would mean communication has led to benefit. S of dyad is better than S max. Anything below 1 means communication has been counterproductive. People have put time and energy and effort into talking to each other, but their performance has actually been worse than if their better member had taken care of all decisions. Right? Okay, so this is one of those things, the opportunity cost of collaboration, which we haven't really been looking at, but I'm very curious to look at and see how that is. So the four models I've plotted here, and you can see them. The flat one at 1 is the expert rule. The dash dotted one is the coin flipping. And the red and the green are actually the ones that we are more interested in. The red is the weighted confidence sharing, the linear combination, which, as you can see, has a nice relative linear behavior. And the green one is the signal sharing, the one that is similar to multisensory integration. Now, how does the data compare to these for predictions? Well, we already know that the expert rule and the averaging or coin flipping would have been wrong, because I have already shown you that there is a collective benefit. But when we look at these, this is the first initial group of data points that we had, the first 15 subjects that we had. The first 30 subjects, which gave us 15 groups. What we saw was that these 15 initial groups that we looked at, actually they all fall on the upper part of similarity regime. And that is more or less expected. We give people visual stimuli that are relatively, that are exactly identical to each other. We pre-select people to be visually and optically like 10 out of 10 in their vision. We do not want anyone who has visual problems. Therefore, we expect them to their performance to be roughly equal to each other. So they happen to fall on the side of the curve that the confidence sharing and the signal sharing models actually make identical predictions for. And if we go back, like if I assume that S1 and S2 are equal, this and this are exactly the same. They result in exactly the same thing. So, and they actually reduce to the same thing if S1 and S2 are equal. So that's why the closer they are to each other, the predictions are more and more indistinguishable. What we needed to do was to test people under regimes, under a visual perceptual regime where one person would be much better than the other person. And in order to do that, what we did was we brought people into the lab and we gave them their task. But we did not tell them that one of the two people would be receiving a lot more noise than the other one. So the signal strength would be, the magnitude of the signal would be the same, but there would be a lot more noise embedded in the distractors as well. As a consequence of that, what we expected was the person who gets the noise would have a much flatter psychometric function, much wider the expected distribution of noise. And that should give us pairs whose opinions are very different in terms of their reliability. One subject who has a very high reliability and the other one who has much lower reliability. And what we see indeed is here shown in data points in circle. These are the ones who have, as you can see, first of all, most of them happen to be on the left side of the similarity axis. That means that the application of the noise has worked, and one subject is much worse than the other one. And the other point is that these happen to be, on average, most of them, below the no benefit line. And that tells us that if we combine decisions from two sources or two human decision makers who are very different in their competence, and they are combining their decisions by combining their uncertainties, as we have seen, then there is a big danger. And that danger is that we actually may come across the too many cooks will spoil the broth. So what I think this graph shows us is one of the things I promised you, which is what is the limit condition between when a cooperation works versus when it doesn't. And what it tells us is that it's the difference or in competence. The similarity of competence between two decision makers is very important. For two heads are better than one happens when you have two observers who are similarly competent. And too many cooks can happen when one observer has a much higher, much better reliability than the other one. Now, the interesting point is that there's actually the red curve that we see, gives us a quantitative boundary for what is the divergence in competence above which it is better to apply the expert rule. And this is what we have. Of course, the exact number is about 0.4 here. But I think it is possible to extend this to other domains. And I'll show you some data similar to that. But the exact position of this boundary for useful communication, I think is very much dependent on the choice of your model and your task and the contingencies of what people are actually making joint decisions about. By the way, this is Dan Bang, who is here in Oxford, has been doing a PhD in Department of Neuroscience and Psychology, and this is Karsten Olsen. These are they used to be my research assistants in Denmark when we were collecting these data.
So,
yes?
in terms of your models, then if I remember correctly, that says that the closest model is basically when they rate their confidence.
The closest model is that the communicated information is the z-score of those distributions. The observation is that they combine confidences, and whoever has higher confidence dominates the decision. But the red line here assumes that the z-score is what people communicate. And importantly, if they could segregate the mean from the standard deviation, then we should not see any collective loss here. But that's what we see. So these are two examples, as I said, of tasks that are kind of similar, but not exactly. So we have two people here looking at a sequence of numbers and then estimating the average of the sequence of the numbers. And first they estimate the averages individually, and then they talk to each other and make a joint estimate, and then they get the feedback. In this one, we have a number line task. Everybody gets a line, in this case going from -1,000 to +1,000. And the subject then gets a pointer, like the mouse, to click on where he or she thinks the number -102 actually would be on this line. So the subject's task is to identify the location best corresponding to the target number on that number line. And then they identify that their expected positions, and then they actually make a joint decision as well, like adjusting between the two of them. And you can basically apply a similar analysis and estimate the precision of the performance in the individual level, and the precision of the performance in the joint decision level. The important point here is that both of these are identification experiments. They are not categorical like the previous experiment that I showed you. And you can see that the relationship between similarity and collective benefit also holds here, but empirically, this boundary of where is the right where is the boundary for below which we would not suggest cooperating with each other varies. And I would have no confidence in telling you if these are optimal or consistent with a given optimal, let's say, decision like the one I showed you in the previous slides. I wouldn't put my money on where exactly these are, because this one perhaps more because we have a lot more subjects here. But with this one, the only thing that I would be really sure about is that there is still a relationship between similarity of sensitivity and collective benefit, even when people do not make a categorical decision. But, so the question, the next question we had was, collective benefit seems to depend on similarity of competence. But then we started thinking, why is it that people here consistently miss out on the difference between their opinion and they don't realize that they are doing worse than their better member? Why is it? One of the things, we had two or three, several different hypotheses could be brought up. But one of our interesting observations was this group, which I was there in the lab myself, and this is happening in Denmark somewhere. So with these, like after about 10 practices, I remember one of the two participants turned to the other one and said, "It doesn't look like I'm doing any good. So I'll leave the decisions to you at the joint level, unless you really have no idea what has happened. And then you ask me." And they actually managed a lot better than the others. These were the only ones who completely disregarded the social conventions of joint decision making. And one person excluded himself entirely from the joint decision process. So what we saw in my feeling was that people really try to include each other in the decision making. And that is consistent with a lot of works that we know in social psychology, that social exclusion is painful. People do not like to be excluded from this kind of situation. At the same time, realizing that your opinion is worth nothing is also not that nice. And people would resist the notion that maybe my opinion is just useless. So there's incentive on both sides to avoid this kind of behavior. And we wanted to see if that is really the case. So, and it was, these were Ali's, Ali, who you can see here, was a student in Tehran University about 3 years ago when he started working on this. His starting point was this poem. This is where he got the idea from William Butler Yeats, which was kind of like about the First World War. He said, "The best lack all conviction, while the worst are full of passionate intensity." And then it's, if you look at like all sorts of internet quotes and famous aphorisms that people share in Instagram and Facebook and everything, you see many of these. People complain constantly about how those who know something are always uncertain, and those who have no idea what they're talking about are always very sure about themselves. So the hypothesis that Ali wanted to test was if people actually behave according to how much credit they deserve, or rather than that, they behave based on some sort of prior assumption. And that prior assumption that we were curious about and arising from these kind of things is something similar to what you could call the equality bias. What do we mean by it? I'll show you in a second. So the experiment that they worked on, subjects actually expressed their choice and their confidence. The choice was made by this within this visual display. Each subject got one of these. There was a line and a boundary in the middle. The subject then used the joystick to drag their own marker to one side or the other and indicate their confidence by going far from the boundary or staying close to the boundary. So for example, this would be the subject indicating first interval by going to the left and then going very far left, indicating high confidence. Whereas if the subject went right, but stayed close to the boundary, then the subject would be indicating low confidence in. So first, subjects did this and expressed their choice and confidence in their decision. Then in the joint decision stage, they did not talk to each other. They were just given their confidence levels in the initial phase, and they alternated in arbitrating between the two decisions. And what we wanted to know was if we could quantify each subject's like credit that they give to the reliability of their own decision and to the reliability of the other person. So one thing that we saw, the interesting pattern was you could still, like even here, based on the choices, you could separate people into the less sensitive partner and the more sensitive partner for each dyad. Here the black and white correspond to the less and the more sensitive partner. The y-axis is the probability of reporting high confidence. And by high confidence, we mean confidence that is above the median of the subject himself. Because each subject has a different profile of confidence. Some people are generally overconfident, some people are generally underconfident. So we first calculate the subject's own median and then label the trials as high or low confidence based on whether the subject was expressing more than his own median or less than his own median. And then what we see is that in the trials in which they have been making a correct decision, more sensitive partners are on average expressing more high confidence. This is good news. We want the more sensitive subject to be more confident as well. The disturbing one is that when you're making an error, the less sensitive partners are actually more likely to express confidence higher than their own median.
Sorry, this is based on the individual decision.
This is based on yes, and conditioned on correct versus incorrect decisions
In the individual.
Exactly. So this is already alarming because it shows you that if you're conditioned on being wrong, the less reliable member of the group is likely to be more confident than the other one. So what Ali and Dan did then was that they applied they quantified the overcredit that the subject would assign to his own decisions. In other words, if there is a disagreement between you and me and each of us has expressed some confidence, if I have a unit confidence, how much of confidence I need from you to change my opinion? Is that clear?
Yes.
Okay. So the larger this number is, that means you are more overconfident about yourself. And if it is negative, that means you're actually underconfident and you're not giving yourself enough credit. And what we see in data that we have collected from Denmark, from Iran, and from China, so by the way, this is that the better member of the groups do not give themselves enough credit, but the worst member of the groups give themselves a lot more credit than they should be. And yes, I remember Peter Latham told me that this is empirical evidence for refusing to cooperate with incompetent but confident collaborators. But so what it shows you is that within each dyad, the less sensitive partner ignores good influence from partner, and the better member of the dyad actually takes too much of bad influence. So there is a lot of similar findings in social psychology in all sorts of self-serving and self-serving biases, especially related to this one. Like people are optimistic. If you ask people how many are, like which one of you thinks they are an above average driver, almost everyone, I don't ask you to raise your hands, but I'm sure many of you would believe that they are an above average driver, above average skier, I don't know, and the athlete, whichever you like. The question really is beside the point. We almost always believe that we are above average in whatever it is that we are assessing ourselves. And that could be similar to this, but it wouldn't explain this one, the opposite side of the effect. So the cognitive mechanism that we thought would explain this was that if people have a tendency, a bias to assume equality, if everybody assumes that they are on the right side of that competence to similarity, then assuming that you're equal, if in reality you are not, then the person who's better is actually not doing enough of imposing himself, and the person who is worse is actually taking too, or badly influencing the decision too much. So that's why we call this the equality bias, because the better agent undercredits his own opinion, and the worst agent overcredits his own opinion. And that comes from the very simple underlying assumption. A very simple underlying assumption could explain this, that we just believe that our opinions are just as good as each other. And most of the times, the thing about this is that this is a very good strategy. This is a very simplifying strategy. It simplifies the life of people who want to make joint decisions with each other, if the assumption is actually true. If the assumption is true and you're roughly similar, this makes your life a lot easier, calculations are a lot easier, and decision making is a lot easier. But it's disastrous when you're paired with someone with a lot of like when there is a big competence gap, and you should be careful about that. So this was Ali's point, that these guys were right. But anyways, So, but why is there equality bias? I guess I already talked about both of these points. That one, without equality bias, that the computations necessary for credit assignment in joint decision making become very, very difficult. You would need a lot of memory, you need a sophisticated learning mechanism to learn your own reliability, the other person's reliability, and combine them in a roughly reasonable way. Whereas if you assume equality bias, suddenly everything is a lot simpler. You just compare confidences, and whoever is more confident gets this decision, and you're right. The other one is that social obligations to respect the other person's opinion also translate to equality bias. Our let's say our negative attitude towards being socially excluded means we assume that we are just as rightful or justified to contribute as everyone else is. And contributing to joint decisions is also inherently enjoyable. But then finally, the last experiment that I will talk about is this work done by Uri, who asked, will there be an equality bias if people did not have to commit to an initial decision? But when Uri came to our lab, we had done these experiments. He objected, and he said that the fact that most of person-to-person interactions and joint decision makings, in a lot of situations, people do not commit to an initial decision first. We come to a panel and we discuss different options, and eventually somehow one of the options is taken. So what happens if we do not force people to take one side or the other? The logic over there was that if you do not force people to do that, then people may not insist on their bad information, on their noisy representation of the task, and it may be that joint decisions can do better if we do not ask people to commit to wrong decisions. So what he did was that he compared joint decision making under two conditions. The top is exactly what you have seen so far. The joint decision, the individual decision, and then the outcomes. The bottom is what he called the social influence condition. And people saw the stimuli and then immediately embarked on the joint decision. So they talked to each other without having committed to one or the other choice, and they made the correct choice. Now, the smart thing here is that in both of these experiments, he asked subjects to make joint decisions in all trials, and in odd and even trials, different subjects were assigned to press the button on behalf of the group. So although here people have made a joint decision, we could, given this characteristic of the experiment, we could actually find out which one of the joint decisions each of the two members has made on behalf of the group. Is that clear? Happy? Okay. So, and what is also important is that because we saw that the equality bias was most important for high competence gaps, Uri tested people by only within the condition of low similarity. So within all his experiments, one subject was always much worse than the other one. First prediction that Uri had was that if this is the case, then comparing the accuracy of the joint decision, this white one here and here, his first prediction was if there is equality bias, if more equality bias here compared to here, then joint decisions should be better here compared to here. And that's exactly what he saw. So joint decision, this is the slope of the dyad under conditions of independence when people commit to an initial decision, and under condition of influence when they immediately embark on the joint decision making. Remember that the visual stimuli that they are getting is identical. The information they are getting is identical. One of them is getting noise, the other one is getting signal. Everything in that respect is identical. Even the order of influence and independence is counterbalanced across different groups, so that half of the groups do this first and half of the groups do this second. So, but still, people under influence, people are actually doing better than alone. Then, finally, what he also looked at was the sensitivity of the individuals. This is the sensitivity of the individuals. This is the worst member of the group on this side, and this is the better members of the group. And do I have them? Just ignore these for a second. So the dark gray is the private decisions, the commitments that people made in the independent condition. And we can see that, yes, the worst member, the one who got the noise, was doing much worse than the better member. What is important is that under the influence condition, even this worst member was doing much better than himself when he was pressing the button, right? So the decisions that he made under social influence was much better, and they were better than the joint decisions he made when he had to defend his bad decision. Comparing these two is the most instructive. You can ignore everything else in this graph and just focus on these two. This is when the bad subject with noisy information is making a decision on behalf of the group, having made an initial bad choice. And this is when the same person is making a decision for the group, just listening to the other person without either of them having made a decision. And you can see that he's doing a lot better, meaning that he's swayed by the advice from the other person. They both had that, and his decision is based on identical set of visual stimuli. And he's making a decision on behalf of the group. Everything is the same. The only difference is that here he has made a prior bad decision that he tries too hard to stick to. Whereas here, he doesn't have anything to lose by just going with the other person's decision. I think I'll skip the other bits of the details of this. You can see the paper if you were interested. But really, the core of this slide is the difference between these two, and how committing to a bad decision can make you make bad decisions on behalf of the group as well. So equality bias is mitigated when agents do not have to commit to individual decisions that are likely to be noisy. Anyways, the summary is that joint decision making can be useful. The main quantitative like predictor of uncertainty-based joint decision-making would be similarity of competence. And the reason why confidence that could mislead groups into doing bad things is probably something like equality bias. And if we do not force people to make initial decisions, we may actually get around that equality bias and enhance group decision makings. And thank you so much.